Good morning, and welcome to the second day of the Big-Data.AI Summit. AI historian Pamela McCurdick observed that artificial intelligence started with the ancient wish to forge the gods. Well, this wish, this dream, this desire has expressed itself throughout human history in works of fiction. We find one of its earliest manifestations in Homer's Iliad. And while the notion of creating intelligence has moved from fiction to science, and while this science of artificial intelligence is advanced through its mathematical foundations, dreams and imagination play an important role in inspiring AI engineers across the world. Our opening speaker is the distinguished IBM fellow, Dr. John Cohn. John has been working in the field of technology for over 40 years, and he had the chance to work and collaborate with some of the founders of artificial intelligence. In his speech, he is going to elaborate on what inspired him in the past and what keeps him motivated as he looks towards the future.
Good morning, good afternoon, good evening. I'm John Cohn, coming to you from beautiful Jonesville, Vermont, and I'm here to talk to you about Back to the Future with the MIT IBM Watson AI Lab. I've had a great run there because I actually been around the MIT community since 1977. So that's about 44 years. And that's why I think of this as kind of a back to the future story. So let me tell you a little bit more about myself. To the extent that I actually grew up in Houston, Texas during the height of the space race. I was so excited to be an astronaut. And then somebody told me I probably wasn't handsome enough to be an astronaut. But that didn't bum me out too much. I actually decided I wanted to be an engineer. And my mom just found a piece of paper that I wrote when I was 8 that I wanted to be an engineer and I wanted to go to MIT. I got both those wishes. So I have been actually at IBM for 40 years and I actually really love it. I want to introduce you to a couple more people that will help me tell the story just to give a little bit of perspective. The first one is my late father-in-law, Gabe Mariano. He was a first-generation American, and he actually got hired right out of high school and sent to IBM College, where he became a mechanical engineer. He loved building things, making these gigantic robotic machines that helped us build some of our first servers. He spent 36 years at IBM making these beautiful things, but the most beautiful thing that he made was my wife, Diane, who is actually also an electrical engineer and worked for IBM for 8 years. Now, through that span, we've had 84 years of IBM and of this industry. And that gave me kind of an interesting perspective because my expertise actually for most of my 40 years has been in the construction of computing, which is central to the AI story. Our company actually started out by making mechanical computing. We actually made things like meat grinders and calculating scales so that if you said cheese was 3 cents a kilo and you had 3 kilos of cheese, it would do the computation for you. So if you actually looked over the span of 100 years of what the industry has done for computation, starting from those simple mechanical computation, then you started to go to electromechanical, vacuum tube, discrete transistors, which is what I was doing when I started in IBM, and then to what we currently use, which is a complementary metal oxide or CMOS chips. If you look at the span of that 100 years and compared how much compute you could get for a fixed amount of currency, say 1,000 euros, it has continued to go up in a superlinear way. It's really amazing. We tend to think of things like Moore's law or Dennard's law, as we call it in IBM, over this span of about 30 years. Well, it's actually a much longer example. But the reason I'm bringing this up now in the context of AI is that things have changed so fast in this environment. It's important to kind of look at a few lessons from that. And these are actual computers that were made by companies in the industry, including my own. And it was very interesting to see how this progressed. And as you see, it's just continuing to go up, which is remarkable. But it doesn't go up in a smooth kind of way. It actually goes in these points of linear where you're able to do sort of continuous innovation. For example, when I started here in these bipolar computers, they would get faster and faster and faster, but they'd get hotter and hotter, and they started catching fire and melting. And we were told that was bad for sales. I'm a technician. What do I know? But it turns out that sometimes in the course of these technological changes, you have to go through these disruptions. These are these moments where all of a sudden nothing works. I remember when these things were starting to go too hot, these bipolar chips, we actually had to shift down to another technology, CMOS, which we continue to use 30 years later. But as you see, we had to kind of bridge this gap. These companies that were able to move across those gaps live to tell the story another day. The companies that couldn't make these leaps actually were kind of left and either went out of business or no longer built computes. It's a very, very interesting analog for the times that we find right now. These are very unprecedented times in the world right now. And the kind of challenges that we face, I think even as companies and as people, is that when you're faced with these disruptions, whether it's world pandemic or anything, the right thing to do is to kind of move boldly forward, even if you don't know the future. So I find that pretty interesting. But I find that this whole sweep of the increase in compute, which was amazing for the last 40 years that I've had a front row seat, is actually very interesting because it's behind what we're now seeing in the growth of artificial intelligence. And I will tell you, as someone who's been in the industry for more than 40 years, what's happening now in AI is more exciting and moving faster than any other technical revolution that I have seen in my decades. Now, it's a very, very important and fundamental change. But before we lose track of it, it's also very interesting that it's a lot of fun making those giant leaps. When I think about how compute has advanced and how AI have kind of advanced together, a lot of it is actually going around my favorite topic, which is play. I mean, when I was at Carnegie Mellon doing my PhD, I was around the team that actually built one of the first really AI-ish chess machines. It was, and then when IBM actually started collaborating, we built something called Deep Blue, which was actually the first computer that could beat a world grandmaster in chess. And that did amazing things to advanced compute. I was very honored to be able to work on the IBM Watson program in the early 2010s. And in 2011, as many of you probably remember, IBM was able to compete in an American word show called Jeopardy, which was just an amazingly difficult task. It was riddles, and you had to answer the in question form, and it was about anything: science, sports, history, etc. And this computer that we built, I worked on the hardware, and 1,000 of my colleagues actually worked on hardware and software, etc. It was really to play a game, but it did more to advance aspects of AI, especially around model representation. And even today, my colleagues in the Haifa lab of IBM Haifa lab are looking at, well, I don't know if it's a game. In some parts of the world, arguing is a game, and we're actually building computers that actually can argue with a human, or debate, maybe in a more polite way, to be able to take any position and defend it based on being able to go out and look at the world, in an unbiased way and make an argument. So it's very interesting to see how this important kind of this transformational technology is all done through play. My personal experience with that is I was lucky enough, as I was working on chips, not only was I working on compute, for example, for like the Jeopardy program, I was actually working on video games. And this is, for example, the PlayStation 3. This was Xbox 360. This was Nintendo Wii, perhaps your parents' generation of video games. But these were like supercomputers that would go under Christmas trees. And it was so amazing that even though these were incredibly complicated tools, they actually set the ground. These kind of consumer supercomputers actually drove down the cost of compute, drove up our ability in things like memory and processing speed. The first gigahertz kind of computers were like there. And it also drove bandwidth. So it's important, even these things, these very serious topics like AI are driven very much by play. And we're going to come back. You see these brown things right there? These are the first graphics processing units, and they factor into my story. The story, though, for AI actually starts before I started. This was in 1956. This was the Symposium on Artificial Intelligence that was held in Dartmouth, just about 100 kilometers down the street from me here. And it was actually a group of scientists from places like MIT and Bell Labs. This is Claude Shannon from Bell Labs, also from MIT. And it's very interesting that our experience, my company's experience, my industry's experience with MIT goes back that far. This is Marvin Minsky, who was by many considered the father of artificial intelligence. He was also the father of my undergraduate roommate at MIT. IBMers were here too. As a matter of fact, that the I'd give you 2 seconds to sort of figure out who the IBMers were here. Well, given the old dress code, this is Nathaniel Rochester, the father of the 709 computer. If you ever get to watch Hidden Figures, a great movie about the space program, he factors into there. But he's there wearing a tie. This gentleman is also from IBM. And together in 1956, all of these great minds came together to talk about the potential for artificial intelligence. Well, the interesting thing about it is it took a long time from that, almost 65 years to this year. Many people have talked about AI, and there were many promise. Even some of the basic things like neural networks that Marvin Minsky, who I knew very well as an undergraduate, was talking about these perceptron networks, et cetera. But it wasn't, we had sort of two, or at least two, what were called AI winters, where AI was about to happen, and then it kind of died out. There were very specific techniques like rules-based systems that were too fragile and too difficult to maintain. And it wasn't until relatively recently, let's say 2012, 2013, when somebody had the great idea to take the compute that was necessary to take a neural network, which is basically a crude model of how an animal brain works, and do a simulator that was based on the graphics processing units in games. And from that point, and let's say it took off at about 2014, the amount of uptake in AI, the hype has actually been delivered. And it's growing faster than any technical trend, like I said, that's happened in all of my almost 50 years of working in this industry, if you count school. Well, I was very pleased when IBM announced the MIT IBM Watson AI Lab, because it really is back to the future. I mean, I can walk around on campus with my eyes closed and still find things. But this is a big investment that our company and many other companies are seeing this as the biggest transformational technology that certainly in the last century. And our lab there, which I'll tell you about in a little bit more detail, has 4 basic missions. It's to look at the fundamentals of AI around AI algorithms, and that's where I work, in the physics of AI, applications of AI into industries, perhaps like yours, like cybersecurity, healthcare, financial services, and also AI for shared prosperity around ethics, et cetera. Let me tell you a little bit more about the program, and then I'll tell you about some of the issues that we're working on as we advance. So the MIT IBM Watson AI Lab is a 10-year commitment by my company and by MIT. It's jointly run. Half of our people are on our MIT faculty and half of the people are on IBM. It's about $250 million of investment in real dollars in terms of people, facilities, and funded projects. Those projects it's very much like a university kind of proposal process where at any one time, we may have we put out requests for proposals several times a year. We have somewhere around 250 proposals that come in, and at any given time, we have a portfolio of more than 50 projects that are done. Instead of this being just simple funding, we actually work hand in hand, and all the papers, all the code, all the patents, et cetera, are done jointly. And for the most part, all of the work that we do, this is to advance technology, is done in open source. We actually have of those projects, we have about 150 people from both sides, from the MIT side and from our lab, which is actually on the MIT, moving right onto the MIT campus. We're a couple of blocks away right now. But also on other parts of our company. And we have a partner program where we work with people from all different kinds of industry. So let us know if you're interested. But what I'm most proud of is that there are 23 departments at MIT in every kind of topic. And we actually have projects with every single one of them, including the humanities, which I think is cool. So what we're looking at is our joint goal is to advance from where we are now, which we would call narrow AI. And these are the ideas of, AI that's done in a single task, in a single domain, but can have superhuman accuracy and superhuman speed. And when you kind of pick up your cell phone and it recognizes your face, you're working with narrow AI. And that's really established. It's amazing how quickly it has become so pervasive, whether it's a digital assistant or a phone or in your car. But where we're the industry is right now is we're kind of in the middle of broad AI. And that is actually multitask. The world has very few things that are just a single task. These are multitask, multi-domain. They're distributed. They have to learn on their own to some extent to be useful. And these could be, this is an example that we're working on sports annotation, but this could be also managing like projects we have for managing hospital operating theaters, et cetera, where there are many parameters that have to be watched. You have to make sure that protocol is followed. You have to make recommendations and work with humans. But the main thing that we're all heading towards is the idea of heading towards general AI. And with general AI, that's what we think about in the movies. It's cross-domain. It learns and reasons on itself. It synthesizes new approaches and has broad autonomy and agency. And you can think about that as full humanoid robots, et cetera. And the interesting thing is there's a lot of speculation is, will humans eventually, will AIs catch up with humans? There's really no doubt that in some degree that they will more than catch up. But when that happens will be very unevenly distributed. And, the projections, I think, are probably kind of looking out 2040s, 2050s. But if we're going to advance that way, and it's inevitable that we do, we have to take precautions. We have to make sure that compute does the right thing. And that's a big part of our lab. We look at the path from narrow to broad to general AI being a set of steps that make sure that AI performs in the way that we would want it to perform, to mimic us or to do our goals. And I'll talk to you about 4 things that we're working on. One is about explainability. That is, AI has to be able to explain to you why it made a choice. And if you need to, be able to correct it in a way that is sort of human friendly so that we can collaborate with each other, humans and AIs. Another is around AI security. And this is not just security. This can be a security in many different setups. This can be, how do you make sure that your data cannot be hacked or extracted? And how do you make sure that AI is being used for good? And this is a big issue because as we start to relegate more decisions to compute, we have to make sure that it does it in a way that cannot be co-opted. Another is ethics, because obviously, if we want to start relegating more decisions, whether it's driving or legal decisions or whatever, to an AI, we have to make sure that it emulates the behavior that we ourselves would like to think that we do. And the other is around sustainability, which is how do we actually make sure that in the process of doing AI, we don't cause ourselves too much problem from hurting the environment. So let me tell you about some of the stories that we're working on. Let's start with explainability. So there is a technology called generalized adversarial networks, which is towards explainable AI. So we have teams that are working on using these AIs, which basically has one part of an AI that is actually synthesizing a problem and one AI that's judging it, and you put them in kind of a loop. And then by specially constraining what's called latent space, the sort of hidden variables that are in the neural model, the sort of simple compute elements that compose a neural network, we can actually train an AI to be able to explain why it's actually making a choice. We can also use those same kind of latent variables to make AI that is controllable and synthesizable. So, for example, my good friend Hendrik Strobel, one of our researchers, has worked on something called GAN paint, which he'll take a photograph and look at a bunch and train this AI on a bunch of classic photographs and be able to then take an element from those and be able to synthesize. If you look on the side picture, be able to take a picture and be able to alter it by using simple semantics that we would know, that a human would do. And it would be able to say, please take out the windows. So if you go look at ganpaint.io, you'll be able to take buildings and actually change these parameters and be able to synthesize new visualizations. Now, this is a really powerful tool for being able to have AI explain and you be able to explain your intent to AI, but it has some unintended consequences like deep fakes. You might look at all of these people and say, what do they have in common? Well, the thing they have in common is they don't exist. These are GANs that are actually trained on human faces and then manipulated using that sort of notion of a latent space to be able to permute various features and still have them pass as human faces, indistinguishable, as a matter of fact. And if you look at videos, you can see that that's a really, really interesting social problem, because if you can't believe what you're actually seeing. So we're also working on technology that will be able to detect these techniques. So it's kind of an interesting mix. In terms of security, I mentioned that as a big issue. You have to make sure that your AI is actually being trained in a fair and purposeful way, because if you're not careful, it's possible to poison your AI models so that they actually they categorize data in a wrong way. And we have a project there. So for example, being able to go in and take a stop sign and be able to, just by simply manipulating the data and the labeling of the data, we can actually get it, instead of recognizing a stop sign as a stop sign, we can force it to be able to recognize it as something completely different. For example, a teddy bear or something like that. And we have a team that's actually looking at how do you subvert models, because that's one way that you have to do. You have to be the good hacker to be able to make sure that your data is secure, and also to be able to measure how susceptible anyone's AI is to that kind of disruption. One fun project that we actually have is using this sort of model sensitivity detection to be able to subvert models. And we have a project that has a set of glasses that can make you be recognized as a movie star. And more recently, we actually have a t-shirt that can actually get you to be falsely recognized, as long as the data is, you have access to the training data. So trying to figure out how we can actually calculate the sensitivity of our AIs to subversion is a very, very important topic. We also were talking about ethics, and we really have to figure out, if we're going to start relegating these kind of important machine decisions, even business decisions, to a computer, it has to be able to emulate our ethics and be able to explain the decisions. Now, there are some clear things. Well, we'll talk about one in a second, but in business, we're always asking to make important life decisions. So for example, who should get a loan, or who should be let out of prison? And one of the things that is unfortunate is that the historical data that humans actually use to build models is actually based on historical bias. So how do we make sure that the AI that we're doing, so this is a project that we actually have with MIT, that we're looking at the fairness on who gets a loan. And if you just base it on biased historical data, you'll continue to promote the biases of the past. So we're looking at ways of determining the fairness of the training so that it represents what we believe the right fairness to be, not what historically has been proven, which is already containing the bias. As you can appreciate, just trying to get computers to emulate our ethics, you first have to decide on what we all believe. And some things like this kind of fairness are cut and dry, but not everything is. But it's a very interesting thing, because it's something you can't do by opinion. And the more important decisions that you relegate to a computer, the higher stakes. So for example, the one that's first comes to mind is, you can look at automatic driving. And the more that we allow a machine to be able to decide on whether I'm going to make a decision to hurt bystanders or to hurt the people who are driving the car, that's a very complicated thing. How do we actually decide what the right ethical calculus is, for lack of a better word? How do we explain the decision making? How do we make the right trade-offs? And how do we assign the right accountability and responsibility? Who owns those decisions? And so it's an incredibly complicated topic, but we're looking at it as scientists and trying to figure out, how do we make sure that we can codify, enforce, and explain all reasoning in these kind of things. Now, it's very interesting because as you talk to people with AI, these kind of complicated situations arise all the time. But what's really complicated is how do you weigh the cost of what won't happen? And if you just look at air travel over the last 3 decades, while terrible things still happen, air travel is so much safer because of the level of automation, including AI. So it's a very, very interesting topic in sort of computational ethics. Now, the final kind of consideration that I'm very involved in is, AI right now, at least the idea of supervised learning, where you have lots of labeled data, a lot of the experiments that we have right now, trying to train on that, it requires a huge amount of data and a huge amount of computation. So, for example, the big language models that some companies are coming out with now, to train one of those models, like a GPT-3 or something like that, can produce more carbon than actually a car does in 5 car lifetimes. And you think about that, you're going to be training it a lot. I mean, these things have great utility, but we need to think about differently. How do we actually do AI computation so that it doesn't start to become a climate issue? There's projections that say by the end of the 2030s that AI could be using a fair bit of the world's energy, and we have to stop that. So a project that we're working on is a project called Satori, where we've built an AI cluster, which is one of the greenest in the world. Satori means sudden enlightenment, but it's actually the name of my second dog, who sadly passed away this year. They're just a cute dog. But her compute was actually the number 4 when it came out up until early 2020, was the number 4th greenest computer in the world for supercomputer for AI computation. And it actually exists in a place called the Mass Green High Performance Data Center, which, more importantly than just how efficient the machine is, that data center runs at 97% renewable energy, mostly hydro. And that is about 70 times more efficient than an average data center. Just by comparison, if you took one of the benchmark workloads that you would run to see how big how well a computer was running, if you ran that computation on Satori in its Mass Green High Performance Data Center, the amount of carbon, since I'm from Vermont, I would say is about just less than 5 maple trees. If you did that same compute in an average data center with the same compute capacity in the average mix of energy in the United States, for example, that's more than 280 maple trees worth of carbon. So it's not that everyone can actually have the greenest supercomputer, but what we're using this to do is to give feedback to people who are running software on our machine, to tell them how much carbon each of those runs were. Now, what's going to actually happen, just like carbon credits for travel, you can actually start to then back out. So you can change, how many hyperparameters you use, how many runs do you do, and eventually to get to less reliance on supervised learning and to start using semi-supervised or unsupervised learning, more like an animal does, and then to be able to make these calculations and these trainings much more efficient. And I want to end on the note, I mentioned how important play was in driving, the advance of AI, just the ability to use graphics processing units was what made AI work. Well, one of the things that I'm doing at the lab, in addition, I work on projects like how much AI can you fit in a very small chip. So I'm trying to bridge between what I knew in the past and what I'm learning about AI. But I also think AI is, because there's so many complicated conversations about things like ethics, it's really important that you get people, especially students, to start to be more interested interested, so we can have more engaging conversations, more nuanced. So I have been really working on what can you use AI for play, and I want to give something to you. So get your phones ready if you can, because I can actually, if you look at that, the URL at the bottom, it's called ibm.biz/Veriman. This is a simple AI program. This uses TensorFlow and a pre-trained network called PoseNet to make a musical instrument that you can run on your phone, tablet, or computer. And I use this to engage students. So, as you can tell, it's kind of somewhat beautiful music. But it also can be used to control the world, like I build TensorFlow. This is an AI. Tracing my body, tracing my face, up and down, and if I move them left and right, it makes it louder, and I can actually use that. Now, if you take this, oops, I somehow if you take a picture of that QR code or look at ibm.biz/Veriman, I'd welcome you to play around with this and show it to your friends and your students. 100% secure in that no data leaves your phone. All of that is being done in the compute, and the source code, the GitHub for that, is actually there. I would welcome any input on that in trying to make AI more fun. So we're at an amazing time, and I really welcome all of you and all of your interest in AI. I hope you have a great, great conference, and it's been great talking to you. Thanks very much.